Cool. Hello everyone. My name is Miłosz. I'm the co-founder of Freedots Labs. So perhaps you know our blog at Tech. We write mostly about Go and other topics. We also maintain Watermill, our event-driven library, and we do online hands-on trainings for Go developers. So if you want to learn more, just hit our website. Everything is there. But today I'm talking about something completely unrelated to what we do, which is my hobby, which is making games. And obviously, you don't need a reason to make a game, right? That's kind of the point. But I want to give you one anyway. So, over the last couple of years, I've been reading online communities and forums like Reddit or Hacker News. And there's one topic I've seen appear and again, like almost daily. And it went something like, I used to love coding, it was my passion, but I got promoted to a more senior role. And now the job is about meetings and planning and status reports. And I don't like it anymore. So what happened? Do I need a new passion? What's going on? And this resonated. I felt like this a couple of times in my career. And I figured what helped me was just going back to coding for fun, which we probably all used to do early when learning programming. And I think games are this type of project that's super fun to make because games in itself are fun, and making them is probably far away from what you do day to day, unless you make games, of course. But I think it's a nice opportunity to, for once, forget about patterns and what's the proper way to do things, or architecture and your team, and just have fun with code. And of course, you can make games in proper engines like Unreal Engine or Unity, but I feel they come with this kind of bloat, and they are heavyweight, and they make you make things a certain way. So you have to learn how they work. And it's not really the fun part for me. For me, the fun part is just making things how I like it. And I hope you all agree with me that writing Go is fun in itself. So why not join both things? So a couple of disclaimers. First of all, I'm a hobbyist, so I never worked on a professional game before. I can just tell you what worked for me, what I like doing. I may say something stupid. I figured that learning how games work takes some fun out of playing them. So if you like playing games, this is fair warning. But on the other hand, I think making them is also tons of fun. So hopefully it makes up for it for you. And finally, I focus on 2D games here because they are lots of fun and simpler to make than 3D games. Although some concepts are very similar. And I will go through many code snippets and examples and concepts. So I have all the materials at the end, so you don't need to try to remember all of it because there will be a lot of it. Just wait for the end for the link. So I'm sure you know what a video game is. You probably played some before. But a more interesting question for me is, what is a video game in a software sense? You probably know how a CLI application looks like in Go, or how an API server looks like in a general concept. But what is a video game as a software? So for me, it was something that took me a long time to grasp. And it started when I wanted to make my first game when I was a kid. And for some reason, I remember I wanted to make this racing game like Need for Speed. And so someone told me programming is how you make games. So I learned some Turbo Pascal, and soon I had my first game running, which looked kind of like this. So it was the classic guess the number game, which looks super boring, but to be honest, it was fascinating for me. It was super cool and got me interested in programming. But I had no idea how to go from displaying those lines on the screen to having a car that goes around, you can control it. And back then there was no YouTube, just those books with not so good translations, as Daniel mentioned before. So it took me a long time to grasp it. And basically I want to tell you what I wish I knew at the very beginning, so it's easier for you. So let me show you a game. The game is about a gopher enjoying coffee by the sea. And then some nasty crabs appear and like disturb him, and they end up squashed. But as you can see, it's a bit choppy, like lagging. We don't know what's going on. So let me speed it up a bit. Okay, now it's a bit better, and you can see the gopher gets rid of them by jumping on them. It's a smart move. But still, it kind of lags, right? It's not as smooth as it could be. So let me try once again. Okay, now it's much better. So you can see like the movement is actually smooth right now. It looks like a proper game, except for the lags that I guess come from video recording of my screen. But other than that, it looks much better. So, of course, all three are the same game. And the difference is they run at different FPS, so frames per second. So the first one ran at 1 frame per second, the second one at 5, and the final one at 60. And you probably know the term FPS either from playing video games or from movies. And it turns out a movie and a game is a very similar concept. And you probably know that a movie is basically a very long collection of images that are displayed one after another, and so fast that our brains can tell a difference, and it seems like the picture is moving. Usually 24 frames per second or 60, or it depends on the movie. So it's sort of an optical illusion, and a video game is a very similar concept. And for a movie, we have this pre-rendered set of frames before we play it. So for example, this is the IMAX film for Dune Part 2, which makes you realize how many frames go into a single movie, probably like hundreds of thousands of frames. But they are pre-rendered, and you just play them, and you can enjoy the movie. But the difference in games is that we don't have those frames at all, because then every play will be the same as before, so it's not really fun. So because we don't have those frames, we simply need to generate them on the fly, and ideally do it 60 times per second or more, so it looks smooth. And basically this is the idea behind games. And in terms of code, a game could look like this. So games are basically infinite loops that draw frames over and over on the screen. That's all there is, except, of course, the draw frame inside is quite complicated. There's some stuff happening that renders the pixels and contacts the graphic cards, API, whatever needs to happen to put the frame on the monitor, actually, in the window, on any platform you want. And honestly, I have no idea how it works, and I don't need to care, because that's what we have libraries for, right? So in Go, I like to use a bit engine, which is a 2D game engine. And what I like about it is that it follows the Go spirit of being a lightweight library instead of a big framework. So it doesn't force you to make games a certain way. It just gives you a nice API you can use, and then stays out of the way. And to get started, you just implement a single interface, the game interface, which has 3 methods. That's all it takes to start. And since we started talking about drawing frames, let's focus on draw first. So it looks like this. So we have just a single argument, the screen, of type Epton image. So as you can tell, this is a regular image, nothing special. And an image is simply a collection of pixels, like you can think of an image file on your disk. Right? So we have some pixels with some dimensions like width and height. That's all there is to an image. And if you run the method with nothing in it, the result is this. So pretty much black rectangle. And this black rectangle is exactly the screen that gets passed to draw. And at the end of the draw method, what gets drawn on the screen is the frame you display to the player. So let's draw something on the screen, right? So we can use the screen draw image method that takes 2 arguments and another image of the same type and some options. So for example, let's say we have a Gopher PNG file on the disk. We can load it to a variable. And I won't dive deep into how loading assets works because it's kind of simple and boring. And then in the draw method, we can execute screen draw image, passing the Gopher as the first argument, and then skipping the options, this passing nil. And the result is this Gopher drawn in the top left corner of the screen, which is the default position of images. And now what you need to understand is that the screen starts empty every frame. So every time the draw is executed by a bit engine, the screen you get is this black rectangle. And whatever happens next is what you draw on it. And this method is executed at least 60 times per second, sometimes more, depending on many factors like your monitor refresh rate. Basically, it's up to a bit engine to do it. So you don't need to care. And when I first learned about it, it made me realize, like, wow, computers are actually fast. And all this drawing happens over and over in a tight loop, and it works. That's pretty cool. So let's move around to make it more interesting. So to move the image, we use a coordinate system that's similar to what you might know from mathematics, except the y-axis goes downwards instead of upwards. So the top left corner is the 0, 0 point, and if you want to go right, we increase the x position. If you want to go down, we increase the y. And if you go by negative values, you can go left and up. So for this, we need options. So we create them like this. It's simply a struct from a button called draw image options. And then we use this translate method that looks like this. So we translate the image by x and y. So for example, let's say you want to move the Gopher 300 pixels to the right and 50 down. So we call it translate with those values, and then we pass those options to the image. And the result is something like this. So our Gopher got moved more to the center of the screen. And the position we specified is exactly the top left corner of the Gopher image. But what is this GOM thing before translate? It looks kind of cryptic, right? So this is a geometry matrix, which is the matrix you might know from mathematics as well, and it has some nice features for calculating things. So let's learn some algebra now, right? No, of course not. No one cares. This is boring. At least I don't care. When I write a game, I want to move images around, not learn about math. Of course, math is important for games, but we're just having fun now, so whatever. So instead, I like to think about it as copy pasting an image in a graphics editor. So you probably know that when you copy paste an image in an editor like Photoshop or something, it gives you this rectangular selection around the image you pasted, and before it gets like kind of frozen in the image, you can manipulate it. You can move it around, resize it, or rotate, or whatever. And this is kind of how I like to think about it. So basically, draws the image in this default position, and then if you manipulate the options, the GOM, it gets drawn in a different way. And if you think of it like it, you don't really need to understand how it works underneath, how the matrix works. And the codes to GOM are relative, so we can have multiple of them. For example, if you move the image by 10 pixels to the right and then by -3 to the left, it will end up on the 7 pixels to the right. But of course, the player won't see this movement, right? Because everything that happens in a single draw method produces a single frame. So the end result is what is displayed, but those movements don't count. And the drawing of the order of drawing matters. So let's say we want to display a background behind the gopher. So we have to draw the background first. So we have two draw image calls, first with the background, then with the gopher. And end result is something like this. If we did it the other way around, the background would just cover the gopher entirely, because it works in a sequential way. And if you draw multiple images, you want to start the OP from scratch. So just start with clear options, so they don't interfere with each other. Sometimes you might want to reuse them in specific cases, but that's only when you know what you're doing. So by default, stick to starting from empty value. Okay, so let's look at scaling images, which is simply resizing them. And there's this GOM scale method that takes X and Y similar to the translate. And one is the baseline, so you can resize the image to be like smaller or bigger if you want. For example, here I pass 2.5 for both, so the gopher will end up, bigger horizontally and vertically, and we have those huge eyes on the screen now. And again, the order matters. So let's say we want to scale the gopher twice and then move it to the right by 300 pixels. So you can do something like this. And this is the end result. Makes sense. But what if we did the opposite? So we use the same values, but we first translate the gopher and then scale it twice. So exactly the same, but the other way around. The end result is this. So this seems weird because it's we did the same thing in different order. And the reason is the scale is based on the 0, point. So in other words, if we first move the gopher, it's kind of like you would move the selection together with it and then scale the entire thing, so it becomes in a different place. So to make it more clear, this is the animated way. So here we first scale it and then move it, which is what we want. That's nice. And then the other way around, you can see the gopher gets bigger and goes off the screen. Long story short, translate last. Most of the time, this is what you want. First scale and then move it. Another thing is rotation. So you have this rotate call on GOM, which takes an argument in radians. I actually prefer working with degrees, so I have this simple mapping function, but you can use whatever you want. So for example, this one rotates the gopher by 90 degrees clockwise, and the end result is this. Okay, so something went wrong because we can see the gopher, right? So what happened? Like, let's see this in slow motion. Okay, so we can see the gopher gets rotated by 90 degrees, but it goes off screen, and the reason is rotate uses the 0, point as the pivot, or kind of the hinge around which the image is rotated. And this is not what I wanted. I wanted to rotate the gopher around its center. So around this point, somewhere near the coffee cup. And it's actually quite easy to calculate this position. I just need half of the width and half of the height of the image. So to do that, I can use the bounce method on the image, which returns the size, and then just divide it by 2, so I get half of the width and half of the height of the image. And then I need to do this weird dance of moving the image back and forth before I rotate it. So first I move the image by minus half width and half height. So the point is to align the center of the gopher with the 0, point of the screen. Then I make the rotation, and then I have to move it back so it appears as if no translation happened. And the end result is this. So this is what I wanted. And I know this is probably a bit confusing at first, so this is slow motion. Maybe it's more clear. So of course this doesn't look like this for the player because it happens in a single frame. But the point is, we want to align the gopher so its center is on the 0, 0 point of the screen, and then do the rotation, and then you have to move it back so it seems like it wasn't moved at all. There's a special case of scale, which is flipping the image, kind of like in a mirror, if you scale it with negative values. We have to do the same trick as with rotate, so all the movement back and forth. So in this case, I scale the gopher by 1 horizontally, which just keeps it as it is, and -1 for the y value, which flips it so it looks like this, like kind of in a mirror. You can also manipulate colors of the images that you draw. So instead of calling GOM, you can call methods on color scale to scale the image with some color, and you can end up with this evil red gopher or whatever green gopher means, which sometimes has some cool effects. And a similar thing is with transparency. So you can use scale alpha to change the transparency, which goes from 0 to 1, and you end up with this ghost gopher or whatever. And that's pretty much the drawing essentials you need. So there's the draw method of the game, image draw image, position, scale, and rotation, and color and transparency. So it's kind of the basic things, but I think it's good enough to just start making games. You don't need much more to just get started. And you can combine them to have some cool effects, like this gopher party, which it's pretty low effort, and you can already have much more happening on the screen than just drawing a single image. But so far we generated just one static frame, which isn't fun. So of course we need more than one. And to do this, we have to introduce the game logic, which lets us work with the game state. What is state? Well, it's a fancy name for whatever you put inside your game struct. So whatever data your game keeps, you keep it in the struct, and this is the state. For example, you can keep the player's position as a vector, which is simply a pair of XY coordinates. And then, instead of using those boring hard-coded values in draw, which always end up with the image in the same place, you translate the image by the position from the state, like this. And then in the update, you can change the state over time, which is the key thing. So coming back to the game loop, I actually oversimplified it a bit, because it doesn't only draw frames, it also updates the state before the frame is drawn. So it looks more like this. And update is the other method from the game interface you have to implement. So the simplest one looks like this. So it takes no arguments, returns an error, but usually you don't want to do it because it will crush your app. And very similar to the draw method, it gets called over and over, 60 times per second, and each update is known as a tick. And a build engine by default runs at 60 ticks per second. So the update method is executed 60 times per second exactly. So this seems very similar to FPS, right? But it is actually a different concept. You can have the game running at 60 TPS, but be running at 120 FPS or something like that. You don't really need to care, you just need to keep in mind this is how it works, so that the update will be called over and over again. And this all happens in a single loop. So for now, just forget your routines exist, you don't need them. And this is the simplest update, perhaps, that we can imagine. So let's say we want to update the player's X position by 1 in every tick. In other words, we move the player by 1 pixel to the right every tick, so 60 pixels to the right per second, because 60 TPS. And the end result is pretty boring, but we actually have something moving on the screen. So most of the time you don't want to change the position every tick, but every some time, like spawn a new enemy every minute, or let the player do something only once every 10 seconds. So we need to work with time, but you can't do it using the standard libraries time features. You do it instead using counting ticks. So simply there's this ticks counter in the state, simple integer value, and then in the update we bump it by 1 every tick, and we have some if condition that checks if we reach some value, like let's say 120, which means 2 seconds, because 2 times 60, right? And then we do something like here I flip a boolean value and then I reset the ticks back to 0. And the end result is something like this. So you have to go for going left and right every 2 seconds. But no, it works, but it's not the best API. At least I don't like working with it that much, because you have to keep in mind this calculation of 60 all the time. And you can use a bit TPS function, which returns the current TPS, so usually 60, to calculate it, which is useful, but I like to wrap it with a high-level API, like a timer. So you have this timer struct that you create passing time duration from standard library, which is more useful. And then instead of all those manual calculations and checks, we can have filter methods like update is done and reset. So it's a very similar thing, but it's easier to work with. And as a bonus, you can have this %done method on it to use to scale values over time. So for example, we could have this scale alpha method, and we pass to it the %done of our timer, and the end result is the same gopher going left and right, but now we also scale its transparency from 0 to 1. So it's useful for stuff like progress bars when you want to rely on how much of the timer has passed so far. So of course we need input handling for making the let the player do something with the game. And many systems use events for this. There is no events in Ableton. We just write simple if conditions in the update, like this. So there's this function isKeyPressed, which takes a key and returns true if in the given tick the key is pressed. It's pretty simple. So in this case, we move the player to the right as long as the D key is pressed during the tick. The important point here is that sometimes you want to do something only once per click, and most key presses will take longer than 1 tick. So it will first the press event happens, then the button is pressed for some time, for some ticks, and then it is released. So there are helper functions you can use, like isKey just pressed or isKey just released, which return true only in the tick that the event happened, which is useful for stuff like jumping, when you want to make the character jump only once after pressing the key, instead of all the time while the key is pressed. And a very similar API exists for mouse, gamepad, and touch controls, so you can just use it in a very similar way. So whatever your game does, it will need some objects. So basically it's things that behave in a similar way, or you display them in a similar way, and you don't want to keep the data of them separately, but together. So the simplest possible thing you can do in Go is structs, of course, and this is regular Go code. There is nothing related to a bit engine here. So the simplest object I can imagine has some position and an image, and that's good enough to start. So we keep a list of those objects in a state as a slice. simply. And then while drawing them, we can iterate over those objects and just draw each image separately using the object's position. And in the update, we can manipulate the object's data, like move them to the left here, which makes it easy to just make objects do the same thing, or to create more objects that do the same thing. That's super easy to do thanks to this separation. So we have the logic essentials here. So the update method in the game, state of the game, timers, input, and game objects. And again, it's very basic, but should be good enough to get started. There's also this layout method, and the third method in the game interface. But to get started, you don't really need to understand what it does. It's used for scaling the game on different screen sizes. So you can check the docs once you're ready. For your first game, you can just use the default values here, and it will be fine. So one thing you need to remember about games is they are an optical illusion, right? So for example, take this gopher who's jumping in the air, and you can see, there's some gravity in this world, and there's a shadow behind him, and the wooden deck prevents him from falling into the water. At least that's what it seems like. But in reality, it's just I'm just moving the image up and down with some certain speed, which looks like gravity, and then scale the shadow together with it, so they are aligned. And very often this is what games do. So if you have an idea for some mechanic, you don't really need to implement it as it is in real life. You can do something that just looks like the effect, and it will be good enough. And just keep on drawing images. It's pretty much what the game is. And there's some stuff beyond essentials. So I have some notes about them, and I will go through them very briefly because we don't have much time. So you can use embed for portable assets. If you know the embed package, it lets you compile some files directly to your binary, which feels like it is made for games because you don't need to care about this distribution. Then you just distribute a single binary, like one of the best features of Go. And you don't need to care where your images go. It just works out of the box. So that's super useful. If you want to do UI, there's text draw, which works almost exactly like the draw image method, except it doesn't take an image to draw, but a string and a font. And other than that, it's a very similar concept. So you have something written on the screen. Animations, is a concept that seems a bit complex at first, but basically it's just changing the speed over time, and that's all there is. So it starts with some frames of the animation you need to have, like for this walking zombie. So there are just 8 images that look like they follow each other. And once we load them from the disk, we keep them as a slice. And then in the game state, I keep a timer and an index of the current image. And in the update, every time the timer ticks, I just increase the index and move it back to 0 once it goes out of bounds. And in the draw, I just simply pass the frame of the current index to the draw image instead of a single image. And the end result is this sort of animation. And if you make the object move as well, it looks like the zombie is walking. But it's kind of a simple code change to just have this much more pleasant to look at thing on the screen. Or another kind of animation could be just changing over time the values passed to the drawing options, like this squashing of the crab, which is basically changing the scale of the crab to be like 5% of the original value, which is a cheap trick. It's not that impressive, but the nice part is you don't need a separate image for it, and it looks better than just disappearing from the screen. So you can use it as well. And another common concept is cameras. So you can think of a strategy game where the game world is huge and you can fit it all on the screen. So you need to show just some portion of it. And again, this can be a complex topic, but at the very basic level, it's a simple concept. So you have this bigger game world and this camera position, which dictates what we see. And a simple way to achieve this is to draw the game on a separate image, not on the screen directly. So we can keep an off screen in the game state and the camera position. And in the draw, every frame we draw everything on the off screen instead of the screen. And at the very end of it, we draw the off screen on the screen offset by the camera position. It's a simple translate code. And then in the update, you can manipulate the camera position, like make it follow some character, or in this case, I just move it right. And this is the end result. So it's also quite a simple implementation, a bit naive, but for many simple games, it's good enough. Another common thing is hierarchy. So you often want some objects to follow other objects or to be drawn next to them. For example, for health bars, you want to keep them close to the object they refer to. And the simplest implementation of this is to just keep some kind of size of children on the object, and then when drawing them, you can offset in their position and scale by the parent values. I don't have snippets for this because it's a bit long, but you can find it in the materials as well. I recommend doing this debug mode in your games. So, having some key combination that enables this cheat mode. For example, here I have the colliders of the objects drawn in last green lines. So, which makes it much easier to see what happens and understand why something displays one way or another. Much quicker than recompiling the entire game and then going to the exact place where the bug happens and figuring it out. There's a vector package in Ebitan that you can use for drawing primitives like lines and rectangles and circles and so on. So that's useful for debug stuff. Ebitan Engine supports audio. I don't have code snippets for this because we don't have time, but basically it works out of the box. You can have music and sound effects. The API is quite simple. And it runs on many platforms, which is pretty cool. Like it runs on web using WebAssembly. So you can deploy your game to GitHub pages very easily and just let people play it online. Also runs on mobile, so you can have your game running on iOS or Android, which is also quite easy. Like, I was able to do it with no experience in mobile development before, so it's pretty straightforward. Also runs on Nintendo Switch, which I didn't try before, but hopefully one day. And here we are at the very tip of the iceberg of game dev, which is a super deep topic. We just scratched the surface of Ebitan and game dev in general, and but the good news is I think you're good to go. With the essentials I showed, it should be enough to get you started to write a simple game. And yeah, be sure to check the materials. I have all the code snippets from this presentation running as a tiny game, so you can see them live and see the code for them, which hopefully should be easier to understand what's going on. I also have some open source games I created, so you can take a look. So yeah, here's a link Go make a game, tell me about it. Thank you.